One of the key steps in performing supervised data mining is data partitioning. In predictive analytics, one important question we need to ask ourselves is how well will our prediction or classification model perform when we apply it to new data sets. Also, if there are competing models, which one is the best? This is a very important distinction between the data mining and the traditional statistics approach to data analysis. Students coming from a statistical background may suggest that we use the p-value or r-square of the model to evaluate model performance. The problem with this approach is that both p-value and r-square are measures of goodness of fit, not measures of predictive performance. For example, r-square is also called the coefficient of determination, which measures the percentage of variance in the target variable that is explained by the model. So it does not tell you about the model's predictive performance on new datasets. Furthermore, a major shortcoming of p-value and r-square statistics is that they are derived from the same dataset that gave birth to the model, so their evaluation of model performance will tend to be more optimistic. When the model fits the data well, there can be two possible reasons. First, the model is superior and has captured all the right patterns and relationships in the data. And second, the dataset just happens to match the model very well. The second reason is what we are worried about. If the dataset used to build the model happens to match the model well by chance, when the model is applied to a future dataset, it will perform poorly. Imagine that you are the director of a new movie, and you are also being asked to be the critic of the new movie. What are you going to say about the movie? Well, of course, you are going to say that it's a great movie, because you made it. The only fair way to assess the quality of a movie is to ask a critic who is not involved in the production of the movie to review it. So in the same way, using the data that gave birth to the model to evaluate the performance of the model will produce assessments that are too optimistic. Therefore, in data mining, we use a technique called honest assessment, which is the gold standard for evaluating how good the model is going to be when it is applied to a dataset that it has never seen before. This technique involves partitioning the dataset into at least two partitions, training and validation datasets. We use the training data to estimate the model, and then use the validation data to assess the performance of the model. By using the validation dataset, we are testing the predictive performance of the model on a dataset that has never seen the model before. So the assessment would be relatively unbiased. In order to make sure that the validation data is unbiased, we tend to use the random partitioning technique to randomly select a portion of the data to be the validation dataset. When this two-way partitioning technique is used, we tend to partition 60% of the data as training dataset and 40% of the data as validation dataset. In some cases, a three-way partitioning is required. For example, if multiple models are produced using the training data, based on the model's performance on the validation dataset, we realize that one of the models, Model 2, is the best performing model based on its predictive accuracy on the validation dataset. So we will select Model 2 as our final model. Is the predictive accuracy from the validation dataset the accuracy that we can expect when Model 2 is applied to a future dataset? Well, not necessarily, because maybe Model 2 is selected simply because the randomly selected validation dataset just happened to match model 2 better than any other models. Therefore, we need to use yet another unseen dataset to get an estimated predictive performance of the model on future datasets. In this case, we tend to partition the data into 3 partitions: training, validation, and test datasets. The test dataset will be used to measure the performance of the selected model on unseen data. When we use the 3-way partitioning, we tend to partition 50% of the data into training, 30% into validation, and 20% into test dataset. No matter whether we use the 2-way or 3-way partitioning, we always leave the largest portion of the data for training in order to have sufficient data to build a solid model. To summarize the data partitioning technique, we can partition the data into 2 or 3 partitions depending on the situation. We use the training dataset to find patterns and construct the model or a set of candidate models. We use the validation dataset to evaluate the performance of the model, or in the case of multiple candidate models, we use the validation dataset to select the best model from the candidate set of models. Finally, we use the test dataset to measure performance of the selected model on unseen data. Partitioning data is an allowable luxury for data mining because we tend to deal with relatively large datasets in data mining. Without a relatively large dataset, data partitioning would not be possible, or at least not very effective. Each partition must have sufficient data to ensure the effectiveness of model development and assessment. While partitioning the dataset into training and validation is usually mandatory in data mining, the test dataset can be optional. When creating a test dataset is not possible, sometimes we can get away with not using a test dataset by using the cross-validation techniques. We will discuss this option when we discuss the individual data mining techniques. In addition to providing honest assessment, data partitioning also allows us to optimize the complexity of the model to avoid overfitting. What is model complexity, and what is overfitting? Well, let's look at an example. In this slide, we have a set of data shown as black dots. Each dot is an observation or case in the dataset. As you can see from these dots, there is a pattern in the dataset. The data tend to go up first and go down and then eventually up again. The 3 lines in colors red, blue, and green represent 3 candidate models to fit the data. The model shown in the red line fits the data almost perfectly. It fits the quirks or noise of the data as well. The blue line fits the data least perfectly among the 3 because it barely captures the pattern in the data. The green line is what we call the just right fit because it fits the pattern in the data but not the quirks or noise. If you try to develop mathematical functions to represent the 3 lines, the function for the red line tends to be the most complex or with the most number of variables, and the function for the blue line tends to be the least complex. So as you can see from this example, having a model that's too complex or too simple can either overfit the model or underfit the model. And both problems can lead to poor prediction performance of the model. Remember, the purpose of predictive modeling is generalization, which means generalizing your model to best fit unseen or future data sets. Now you may be thinking, what is wrong with a more complex model that fits the data well? Well, let's take a look at another example. This example shows you a classification problem. In this case, we are trying to create a model to classify future cases as either blue cases or red cases. We have partitioned the data into a training set and a validation set. To make it simple, both partitions have 200 total cases or dots. Using the training data set, we have developed a model that can best separate the blue dots from the red dots as shown here. The cases in the portion of the data above the line or the model are classified as blue dots, and the cases in the portion below the line or model are classified as red dots. The model performs quite well because there are only a very few number of cases that are misclassified, meaning blue dots in the red class and the red dots in the blue class. And if you count the number of cases that are misclassified in the training data set, there are only a total of 19 misclassified cases in the total number of 200 cases in the training data set. Please feel free to count them if you want. Now let's look at the picture on the right, which shows the validation data set. When we apply the same model to the validation data set, one thing you will notice is that there are a lot more misclassified cases now. If you count the number of misclassified cases, there are a total of 49 misclassified cases among the 200 cases in the validation data set. The large differences between the training and the validation data in terms of misclassification is caused by something called overfitting. It means that the model fits the quirks and noise of the training data so well that it fails to generalize to unseen data sets, such as those in the validation data set. So how can we improve this? How can we reduce overfitting? Well, let's look at the next slide. This slide contains the same two data sets as in the previous slide. The only difference is that we have a much simpler model to separate the blue dots from the red dots. The model is simply a diagonal line. If you check the misclassification of the model in the training data, it is quite larger than that of the previous model. The number of misclassified cases is 34 in the training data compared to only 19 in the previous case. Now let's look at the model's performance on the validation data set in the picture on the right. Well, if you count the number of misclassified cases, it is 43. Okay, there are two observations that I want you to pay attention to here. First, the difference in terms of the number of misclassified cases is much smaller between the training and the validation data sets in this case compared to the last slide. This suggests that the simple diagonal line model shows a much less severe overfitting problem. Second, since we used the performance of the model on the validation data set to determine the effectiveness of the model, the simpler model resulted in a smaller number of misclassified cases in the validation data set, 43 versus 49 in the previous slide. Therefore, the simpler model should be considered a better predictive model in this case. So what have we learned from these examples? First, the model that fits the training data set best may not always be the best model because it may fit unseen data sets such as the validation data set poorly. Second, more complex models tend to suffer from the overfitting problems more severely compared to less complex models. So how do we identify the optimal complexity for the model? Well, let's look at the next slide. The other important use of the data partitioning technique is to help us find the optimal complexity for the model. For most data mining problems, we can build an array of models ranging from very simple to very complex. Model complexity is often reflected in the number of predictor variables involved in the model. The more predictor variables involved, the more complex the model is. As you can see from this diagram, when we increase the number of predictor variables in the model, or increase the complexity of the model, the error rate of the model tends to decline because the model would fit the training data increasingly better. But are we getting better models by increasing the complexity of the model? Well, that needs to be judged by a different data set that the model has never seen before. In the case of data mining, the validation data set. Now, when we apply this model to the validation data set, what you will see is that when we add the error rate of the model on the validation data set to this diagram, it tells us a very different story. The error rate would initially decrease as we add more predictor variables to the model because we are capturing the patterns or relationships with these important predictors. But as we add more variables to the model, which may be less relevant or generalizable, the error rate starts to increase. The trough of the error rate curve for the validation data is the sweet spot for model complexity. It tells us that beyond this point, your model is simply trying to model the quirks and the noise in the training data, which can lead to the overfitting problem. Therefore, in addition to providing an unbiased assessment of the predictive performance of the model, the validation dataset can be valuable in helping us find the optimal complexity of our model. We will use this important feature of data partitioning in many supervised data mining techniques, such as regression, k-nearest neighbors, and decision trees in future lectures. So to summarize, data partitioning is a very important step in supervised data mining. It can help us to provide an unbiased assessment of the model predictive performance, and also it helps us to identify the optimal complexity of our model.